So let's resume from where we stopped last time. So I have here RK that I have defined, and these XK are my parameters, either material parameters or the geometric parameters, and these are basically random parameters. So with them, inserting those values of R at various points K, we can find out our resistance equation. And then if we have sufficient number of points, if you have take for sufficient number of K values, if we can use sufficient number of K values, then we can have a huge data set of RK, and with that we can actually plot our probability distribution curve. We can get the probability distribution of RK like this. If we have sufficiently huge number of data points where I'm varying my material parameters, my geometric parameters, if I'm varying it sufficient number of times, I'll get various values for various combinations of xk's, x1, x2, x3, xn k's. Let's say, suppose this is the depth and this is the Young's modulus. Suppose I'm varying depth from 300 to 305. So let's say for any point 301 Young's modulus, let's say just 10. I'm not going into the practicality of it. Young's modulus 10. So for a combination of 301 and 10, I'll get one RK value. And then I again vary, let's say 302, and keeping this as 10, I'll get another R value. So and you can also keep like 310. I've kept constant 310, and then I'm varying the Young's modulus from 10 to, let's say, 12, 13, and so for various combinations we can get a huge amount of RK. We can generate this RK, store it in a matrix or in an array, and then we can actually plot the probability distribution, like how many times a particular value has occurred. Suppose for this combination 310 and let's say 10, 310 is my depth, and let's say this one is 10, Young's modulus. For this combination we got, let's say, an RK value of 50. So for various other combinations also we can get an RK value of 50. There's a possibility that I can get an RK value of 50 for other combinations too. So keeping all the data that how many times 50 has occurred, so I can create a probability distribution curve of my RK, of my resistance RK. Now, using this probability distribution, or using this value of RK, we can also get our failure functions that we already know of. M is my failure function, R minus S. R is coming from RK, so I have a probability distribution of R. Even S, my force that I am applying, might have a probability distribution, but it depends on many various factors. So I can have a probability distribution of S also, and sometimes the failure function is also written as R by S. Z equals R by S, and then we get our failure functions according to it. Now the point is, the general question that comes is, when I'm going to vary this xk values, can I have like any value? Can I vary it from any point to any point? Can I have any numerical values, or is there any rule to constrain it? Yes, there is some rule to constrain it. Why? Because if I give any value, then it might have an impractical values associated with it, and unscientific values associated with it. Like I said, depth cannot be 1 kilometer. I can put 1 kilometer here, I will get RK value definitely, but this is not going to be a very practical scenario. So I have to eliminate, although these values are random, but then this have to come within a range. Only then you will have some realistic values of RK, and then you can proceed. So how to find that? This is what actually Monte Carlo simulation will have. So let's write down the steps that are involved in Monte Carlo simulation technique. Steps involved in, let me write Monte Carlo simulation like this. Monte Carlo simulation. Okay. The first step that I have is generate a random number. Generate a random number from standard uniform distribution. Standard uniform distribution. I'll just explain this to you. So you need to remember this points distribution. I'll just write DSTR. Okay. Now the next step is perform mathematical transformation. Perform mathematical transformation to produce a random deviate. Deviate. Okay. And the next step is use the transform deviate in the experiment. Okay. Now every step we will come to know, we will come to understand very clearly what these steps usually mean. Now before we go into all this technicality of the terms, I'll just try to put it in a very simple fashion. Okay. Now here in my Monte Carlo simulation technique, I have two things basically which I need to keep in mind. Two terms basically. One is my uniform variate. Okay. And the second one is, so this one uniform variate, let me denote it by capital V, or here in this case actually I have denoted by X's, so either I can denote by capital V or X. That's my wish. And the standard uniform deviate. Okay. Standard uniform deviate. The standard uniform deviate I'm going to denote by a small v. I'll put it almost like a nu so that I can differentiate between these two, because as you made out, my handwriting is not that classy, right? So what do we have now? How these things are? So this uniform variate is the one that we are seeing here on top of this here. These are the values that these are the ones we are going to variate, or we are going to go, vary these values. So this is my uniform variate here. Whatever I'm going to vary, the parameters that I'm going to vary, these are the uniform variate. And the standard uniform deviate is a parameter that is going to give rise to the various values that I can deviate from, the range, within a particular range. So it constrains these values so that they don't become some impractical values. So how do I get that? Now the main thing is that what is the different relation between this v and this small v? The relation that actually defines the relation would be cumulative probability. We have already learned about that. The cumulative probability, the capital F, cumulative probability, capital F of V. The cumulative probability of this one is going to be my nu. The cumulative probability of my uniform variate is going to be my standard uniform deviate. Now what if I write this equation, how does it help me? I know my cumulative probability will always range from 0 to 1. Cumulative probability is always going to range from 0 to 1. As a result, this new value, or this small v value, is also going to range from 0 to 1. Now what I have done is I have put a restriction. Here so that my values don't go astray. They do not give some impractical values. So as a result, what we can do is, how can we find out these v's? We have to do the inverse transformation of this nu. and we will get the V values. Okay, so what basically happens is, so this V is like, let's say my here, yeah, let's say this one we have considered as the depth of the beam. So let's say that this is my depth of the beam. This V that I have is the depth of the beam. The depth of the beam, let's say x1k. I will have an inverse transformation of the V. So this small v, I am going to change from 0 to 1. As I am going to change from 0 to 1, I am going to get some depth values. So these depth values are guaranteed that these are not going to be impractical values.